Dear friends, I am your teacher, Patrick Shadin, and together we will do our best to introduce you to more advanced quantitative research methods, and my serious aim here is to have some fun with you as well. This is not going to be a very dry and tiresome course if I have anything to say about it. By the end of this course, you should be able to have a good understanding of quantitative research and also be able to select and use the appropriate methods, tests, be they parametric or non-parametric tests, according to the data you have and the question you are answering. You should be also able to use the most essential multivariate analysis in educational research. And you should most definitely be able to apply this all to your own research. Sorry. Trying to figure out how this works here. Anyway. So how can we do this? First of all, this course is 5 ECTS, however you pronounce that, I don't know. Let's say. So it's a fairly intensive course considering the content we have. We have pre-taped lectures. This is one of them, the first of them. And we will place the links to all these lecture videos and also all the PowerPoints in our Moodle for this course. And you can see the address of the Moodle down below. We will be also using Zoom for distance teaching of the workshops. This is something also new to us. And we want you to be able to do it hands-on. So this is actually the only way to learn how to do statistics, is to do it yourself. And I have never heard of anybody who has a thorough theoretical understanding of statistics but hasn't done any of his or her own. Practical knowledge is really, really important here. If you have a computer, a PC that you are going to use, that's fine. You can install the SPSS from the university app store. And if you need help with that, we have a very good help desk. I think it's simply calling 55555. And then you get our university help desk. You can also contact them via email. And of course, we'll try to help you in any way we can. Also, on the Moodle platform, there's a question and answer area, so you can with any problem or question, you can turn both to us as well as to your fellow students, who will mostly be even more practically oriented than Olli and I am, and be able to solve problems and help you really quickly. There are also computer rooms at the Faculty of Education and Educational Sciences, and those should be available during the hours when the workshops are in the program. We will, besides the lectures and workshops, you will be working on a diary, learning diary of your own, where you will use the data that we will provide, and then create own examples of the key methods that this course contains, and also your own interpretation and explanation of what's going on and how to interpret it and so on. The grading of this whole course is based on this diary, and it's from 0 to 5, 0 being that it's not acceptable. That's very unusual. Okay, materials I was already talking about, you will find at the library, Tabachnik and Fidel, really good stuff. You can also buy it. There probably are even newer editions, and you can most definitely use other statistical books as well. And there's a really good selection of them on the net, and also if you want to go to the academic bookstore in Helsinki, that's perfectly fine. Any of these, you will in your future life, in all probability, be well served by having a book of your own or some books of your own. The video lectures I was already talking about, this being one of them. We also have on the Moodle data where I selected the Scandinavian countries or Nordic countries and Estonia as part of the PISA study, and that data will be available to you, or is it available to you on the Moodle? And we can use it both in the workshops and you can use it in your diaries. So the idea is that we demonstrate something and try it out during the workshops. You will learn the theory in lectures, then we try it out in the workshops, and then you can do it on your own in your diaries. I would, however, like to see you try out something that has not already been taught. So apply, have a look at the data set. It's relatively large, and you can ask different types of questions and use it to answer those questions. You can also find a lot of material, like tremendous amounts of material on the net. Any and all of these you can use and you can share in our Moodle, just to help friends and yourself in the future. Let's create a good material, set of material right there. They change all the time, so you may be able to find a lot of good stuff that we don't even know about. Okay, content-wise. This first lecture is about getting started, a quick overview of basic concepts and methods, kind of pre the real stuff. The second one is about item analysis, reliability, and validity. So important key concepts and one method to try out how your measurements work. Exploratory factor analysis is the third lecture. Fourth is about ANOVA, variance of analysis, and its alternatives if the data doesn't support ANOVA. And the fifth is about regression analysis. And our workshops follow the same content, and we try to keep the content, the lectures and the workshops as close as possible in content, so that it is easy for you to first flipped classroom, first get acquainted with the ideas and then try them out with the teacher and your fellow students. So that's the main idea of the whole program. About the diaries. First of all, you have a front page. There you put your name, student number, the master's program, CE, the name of the course, and for instance, diary, if you are not feeling very creative. Just so that we know what it's all about. And then you write an introduction, what's going on, and then you try out the different methods here. So you can actually follow the same content that I spoke about previously from the lectures, trying out the different methods and explaining what kind of results you get and what they mean. And also you can write this diary in a form so that it's useful for yourself as a future guide in like a cookbook. So if you are going to do a factor analysis in your thesis or later in your life, then you can go back to this and say, okay, let's use this, could do it that way, have to think about this and that and so on. Remember, when you interpret these results, you should also take into account and so on. So you can use this as a guide and future reference when you work. As for sources, I would very much recommend that you write your own diary. In your own words, there's no correct way or exact phrasing or so on that you have to take into account. Think about things, explain it so that you understand it, and then you will also learn it as well as possible. Also, we are really worried about plagiarism, so please be very careful that you are not copying either the words or the ideas of anybody else, except when you write in your sources that the source is so and so, then it's okay. So correct citation is of the essence. Now we get to the beef here. What do we need statistics for? One of my fellow students a long time ago called them fundamental statistics, but that's his joke. What do we really need them for? Well, first, because we have questions and we need to answer them, and we want to answer them in a way that not only convinces ourselves or people who are already believers, who think like we do, but we want to convince people who are non-believers or people who think differently. So we need to have some way of producing answers to questions that are thorough and convincing and don't change all the time. It's not just a question of, okay, this guy said it, Patrick said it, and he's a professor, so he must know what he's talking about. Let's do what he says. No, we do what is correct according to the strongest research evidence we have at the time. And then if we get some new evidence that shows that we have to think differently, then we think differently. And the whole point of the exercise is that this will make you, we hope, better and better in understanding not only how to do it, but also what the results tell you, how you can use them so that you don't overstretch, so that you actually have a very strong foundation in what you are suggesting, how you are interpreting the results. So we get an answer that is hopefully more objective, not only local and short term, not only for today, but has something enduring and generalizable in it. And it may be hopeful thinking. It's not always easy. It's easier to find a quick answer to what's happening now here. Trying to answer the question so that it is a more general answer, however, makes your answer useful for people all around the world. So the difference is, are you going to be a very local guide to interpret the results, or are you going to be a real researcher, real scientist, thinking anew and helping others to change their views? So, in human and social sciences, of which educational sciences are part, we very often have observations, indicators, measurements, tests, you name them. And we need to try to interpret these. So one part of interpretation is it's really, really recommendable, necessary even, to be understandable. We have a lot of people whose understanding of science and research is to produce something that people have difficulties in reading and understanding. And then many people think that that's a sign of good science or wise thinking. I would be of exactly the opposite view. So if you can write something that even your grandmother understands, and something that people in the streets would be interested of hearing, and explain it in a way that makes it living and interesting for them, then we are doing something important. That's the only real way of changing policies, a real way of changing the way people think about something. If they don't understand it, they won't change their mind. And we need to be very careful in how we interpret our results, how we explain them to others, so that we don't fool ourselves, read something into it that is not there, and that we don't fool other people. Every human being is human by default. There's nothing wrong with that, except that the fact is that we are really, really easily led by what we would like to see, what we would hope, what we believe in. And scientific methods, research methods, statistics are one way of trying to sort out what the evidence tells us, not only what we would like to see. Understanding the principles of statistics is also important for your own research. but it is even more important, maybe, in becoming an expert in education. You need to read a lot of other people's research, and you can't just read the stuff that is done by a method that you like or that you find easy or comfortable. You need to try to understand the results and also the background, the evidence there behind the results that are produced in various different ways. So we need to be multi-method. The multi-method approach is better than having just one approach that you are the expert of, so that you can take into account what different types of research and different methods tell you about a certain problem. Then you are able both to utilize and synthesize the different results from different types of research, and you are well aware of the limitations. So instead of just saying, as very many people unfortunately do, especially in the media, just quoting the conclusions of a study, you also think about, is this actually believable? Can you actually use these findings in such different and varied settings as are suggested, and so on? So you get to understand what's going on, not just repeat it as a parrot. Okay, statistical literacy has a lot to do with things like this. Here's a real set of data. Also, I think from the PISA study. Also something that was really reported in Research and Media. And you can see here the OECD average there in the middle. And you can find Finland here. And what's going on here? This is a change between 2003 and 2012 in students' sense of belonging. And this is, in this case, belonging in school. So while the OECD is here, there are countries like Turkey where the sense of belonging has become stronger. Finland is among those where the sense of belonging has become more negative or weaker. And there was a tremendous hullabaloo about this, and the Minister of Education had far-reaching conclusions about what should be done and how should this problem should be assessed and fixed, and how much research and money would go into this, and so on. It's always nice when you suggest that there should be money put into research. However, some money is well spent, other money is not so. So let's take a closer look at this change in sense of belonging in school between 2003 and 2012. Let's look at what it looks like more closely. So here we again have sense of belonging in Finnish students, but now you can see that if you look closely here, strong agreement and less so, but you can see that the differences are not that great. Same number, not that big a difference, not that big a difference. So there is some change, yes. It's not going in the best of directions, agreed. However, maybe that's not such a very, very dangerous change yet. We need to follow it up. Yes, that would be a good conclusion. We need to see what's going to happen in 2015, 2018, but just from this, I wouldn't suggest that we needed to change the Finnish educational system. Okay, sorry, these are articles just to show you that the media is hot on these topics. More of statistical literacy. We have PISA motivation in Finnish students. And here again, this is OECD average. Israel over here, strong motivation, very low motivation. And so even if you don't read Finnish, there are problems with the Finnish students' motivation, and the Finnish students do well at school, so get excellent knowledge and skills, even though they are not very motivated, says the press. Again, let's take a closer look. Something happened. Okay, here we go into this. So it was not general motivation or school motivation, it was performance motivation as measured in PISA. And these are the actual questions asked in the questionnaire of the students. And to make it simple, we have here picked out OECD, Finland, and the United States. And you can see that there are huge differences, but let's think about this for a little while. Here's the first one. I want the best grades in all or almost all of my courses. And you can see the tremendous difference between Finnish students and American students. I want the best grades in almost all of my courses. Now, is that dangerous? No, it's fine. But Finnish kids are well aware that they will almost nobody will almost ever get the best grades in all their courses. So even if they want to have them, it's kind of almost impossible. Having straight A's like in the United States or a row of fives as in Sweden is unheard of almost. So after, in this case, some 9 years of school, they know very well the game and they answer accordingly. It would be nice to be good, but getting the best grades in everything is unreasonable. It may even be counterproductive. I would be stressed out and not get any good results next year. Okay, when I graduate, I want to be able to choose among the best options. You can see that the same thing, performance motivation, is measured, but here the indicator for Finnish students is much higher. So it's almost, it's 80% here, while it's almost 100% in the United States. But anyway, nice to choose from the best options. They know how the game goes and they know how it, so again, I think this just shows that we have a selective system which the students kind of understand, and they have a relatively realistic view of their possibilities and options. I want to be the best at everything I do. This is something that Finnish students really don't say or think. There are a lot of things they can do, and they have a lot of activities outside of school and inside of school, and they certainly enjoy many of them. But if you really talk with Finnish kids, the idea that they should be best in everything, they don't see the point of it. They want to be good or as good as possible in some things. Others they want to do just because of the fun of it. I consider myself an ambitious person. So again, the difference here is clear. the first one, the third one, best at everything. No, not really. Ambitious, yeah, quite ambitious. And I want to be one of the top students in my class. Again, Finnish, and I would think that also Asian students might be in this group. So being the best of everybody is not necessarily the goal. Learning enough, becoming what you want to become, having a good time in your hobbies and so on. The Finnish answer is more complicated than just wanting to perform, and perform. Sorry, that's in Finnish. Always remember how something is measured and what is supposed to be measured. And you can see here that depending on how the question is phrased, how the performance motivation is operationalized, how it's seen in practice, greatly influences from 80% to 36% how many students actually feel that that's what they think like. Okay, so statistics are really important in understanding how science works. And it's also really important in understanding the limitations when it doesn't work. And there are quite a few examples of where it would have been both politically wise and also saved a lot of money and effort if we would have both shared internationally our good results and experiences and the evidence that something works, as well as not gone after a lot of not so strongly evidence-based different types of pedagogies and so on, where people just follow follow what they think sounds like a good idea instead of checking it out. That is why in education we need to know at least most of the common statistical methods and how to use them and how to interpret them. You don't necessarily use them very many times, all of them very many times in your future life. But if you don't know how to use them and how to interpret them, you will be a lot less useful in your work, and you will be less able to change your own mind based on research. Okay. It means also that we should be able to take into account all the evidence. It's called cherry picking. The idea of just choosing the evidence that is for your idea, choosing the research methods that you like and so on. It is very, very important, and I say this again and again during this course, it's really very important that we have an overall view of all the results concerning this, the question we have in mind, and then draw a synthesis where we can both discuss the pros and cons, but also the strength of the evidence based on how the research is done and so on. The question here is that we have as I said, we are very human. We love some things, we hate other things. We shy away from things that we think might be dangerous or difficult or whatever. And that leads us in many cases to be in a bubble, confronted with like-minded people, confronted with the results that we are comfortable with, and so on. And the whole idea of this course is that we need to become so expert that we can move all around the world, encounter different types of research, methodologically different research, and get a grip of the different types of understanding and results, and then form our own opinions, evidence-based. We also, in statistics, research methods, statistics, try to be very, very clear about the assumptions that we are making in our thinking. So, as in the previous example, how something is measured is very important, and important to open up and explain, and also to see, okay, how strong is the indicator or measurement that we are using, and so on. And all this together means that we are better able to evaluate. We talk about validity of conclusions. So if something is valid, then it is a realistic picture of. So if I draw a picture and it's a valid picture of Joe Biden, then that picture should include his how he looks and how he thinks and so on, what kind of personality he is. If it's going to be a valid picture, it's not just a caricature or a very beautiful picture where everything slightly questionable is hidden away. So valid means that it is as good as it gets, and this type of thinking about research is also important. So we try to make our measurements and our analyses and our interpretation of our results as easily approachable and understandable as possible, but we also try to make our conclusions as valid as possible. We don't over, under, or otherwise disinterpret the results to get to conclusions that are maybe popular, but not necessarily valid. Sometimes this means that the researcher says or writes stuff that doesn't get you very popular. It happens, has happened to me as well. And that's quite okay. That's the price we pay for being experts. Important terminology. We talk in statistics about the population. That's the target group of your study. So it may be people, it may be schools, it may be countries in PISA, so on. But target population, the target group of your population, of your study is the population. That's the definition of population in statistics. That is when you are answering a question, it is within the bounds of this population. So if it's Finnish students, for instance, then we always write, okay, the population we are describing here is Finnish students, and we have a sample or some way of representing this population. The population always consists of observation units. That's a difficult way of saying it. More friendly and familiar is cases. And as I said, these cases might be then, for instance, schools, countries, states in the United States. It might be different institutions, universities, for instance, or it may be individuals as students or so on. In research, it is, and this I say carefully, in research, it is really possible and advisable and even recommendable to be lazy. So when you have a population like in PISA, at least you want to have the population you are describing is the student body, 15, 16-year-olds of the whole world, or at least the OECD countries. That's a lot of people. It is of essence that all of these people should not be tested. Why is that? Well, first of all, being lazy here means that you don't have a lot of people working very hard to provide you with the answers. You use the smallest number of cases possible to get the best possible answer. Instead of testing everybody in the world, you test a sample of this population. So that's the first part. Being lazy is one way of protecting the students or the schools, the teachers in the schools, so that they don't get overworked unnecessarily. That's a research ethical point of being lazy. Also, here we protect ourselves. So if there's a way of getting an answer more easily with a better, shorter questionnaire, with a better method, we use it. And if there's a way of selecting a sample or representative sample in a way that protects us from overworking, that's also perfectly fine. A representative sample is a group of cases of the population where each has the same likelihood of being chosen. That's typically something you get when you have a random selection mechanism. So here you can see the squares and circles and triangles and whatever, and in just about the same proportions here in this representative sample, you have the same type of cases. And then you have a not so representative sample, sorry, here below, and there, that's usually a convenience sample. People select the first 50 persons who come, whom they encounter on the street for interviews or something like this. And that's, if you think of it, yes, it's convenient. And I just spoke about laziness. But on the other hand, you pay a price for this convenience. So yes, they walk to you and you can easily convince them and get them to answer your questions and so on. So that part is nice. However, you can't really seriously claim that the 50 first people who answer your questions when you interview them in the street would actually be a representative sample of, for instance, the Finnish population. Well, why not? Mainly because most people from Lapland wouldn't be walking in the street to encounter you, and so on. And if it's during school hours, you won't get the students, and if it's so you will have a very biased sample of if you go about it in the wrong way. And if you have a strong selection bias, then the answer you get represents that sample, but not necessarily the population you are talking about. So both if you have a very skewed sampling mechanism, biased sampling mechanism, or if you have a random selection mechanism, but then not all the people you have selected show up. So, for instance, you randomize the selection of students at the school to have the control group and the test group, but then all those kids who have the flu that day or who don't feel lazy that day or something like this don't show up, and then already the sampling is seriously skewed. It may be that it's a random fallout, but mainly our examples and our findings are that when kids choose not to show up, that's nothing random. Okay, sorry. So we have the population, we take a sample, and then we measure the sample, and we put that data that we gather from this sample into a data matrix. This is important because that's what you are encountering as soon as you open up the SPSS program or any statistical program. You have to have data to do the analysis. Typically, the data is in columns and in rows. And a typical column is, well, let's start with the row. A typical row contains all the observations that you make of one case. So be that, for instance, one student at the school. And that means that okay, let's continue. And then you have the different columns are variables, so everything you measure or get answers, be the gender of the student or the result of the questionnaire or the result of the test or whatever it is, the background of their parents, anything. That would be, all these would be different variables. Variables they are called because they get different or varied results for each and every student. So some people are of the same gender, others are of a different gender. In test scores, you get different points from your neighbor and so on. So that would be already a pretty good starting point. In the cross section here, the blue circle, we call it a cell that contains one observation of one case on one variable. So that's one datum. So a set of data contains a lot of datum, individual items of knowledge, if you want to call it that. So a row has many datums. The set here is a set of data. think we went through that. But please remember this. Ollie will help me in reminding you, but please remind each other as well. There are a lot of difficulties when you want to publish your results if you don't remember this. And I hope that many of you will be researchers, doctors in the future, and research is published in international journals, and they are difficult to get into if you don't know the basics. So data is plural and datum is singular. Usually we talk about data, but people forget that it is a plural form, so you need to talk about it as a plural. All right, getting further into the stuff. We have different types of scales. This is the most easy one. So we have a nominal scale. That means you have 2 or more categories, groups of people or whatever you are represented here. In this case, people, and I have 2 groups, boys and girls, to be really familiar. And you can have different ways of approaching a nominal scale like this. We call it dichotomous also because dichotomous means two types or 2 group scale. D. So it's nothing more difficult than that. Anyway, you can show a dichotomous scale results or a nominal scale result with different graphs, like here. We have the same result in numbers and in the table and in the graph. And you can see the frequency is how many, and the percent is also how many. But in the contrast here is that then you compare with how many out of 100. And it's very basic stuff, but the point here is that you tell the same story with the different pictures and with the table, with the frequencies and the percent. So you choose the way you describe something in the most practical way for the reader, so the message gets across in the best possible way. Yeah. Next, you have a nominal scale in which you have groups. You can have people from Helsinki, from Tampere, and from Oulu in Finland, different towns. They are not ordered in any way. You can order them by something, but then it becomes something different. If you just put them in the order, for instance, of alphabetical order, then it's still not anything other than a categorical or nominal scale. But if you make the variable ordinal, then you order them, for instance, by size. So you would put Helsinki as the biggest and Oulu as the smallest, also by population. So here we would have 12 months and how many people are born in January, February, March, and so on, out of a certain group that are studied. And then we change it into percentages. And you can also already see that something is happening here in the middle. They are slightly higher. So not all months are equal. And you can see it even better here. Some of that may be just random noise. Some of it is probably something that could even be not only typical for Finland and a certain year, but more generalizable. Maybe it is so that people usually get born in the beginning of the summer. More people get born in the beginning of the summer, and less people get born by the end of the year. That's a very rough translation of this result, but you already get the picture. So that would be a typical ordinal scale. There's an order to the months. Other ways of describing your data include different ways of describing what is average for the group that is studied. And here we have different approaches. The most basic one is the mode, which is the typical value, or the value that has most representations. Most cases are of that value. That's the mode. You can see it here. Not a big difference, but slightly higher than others. Then we have the median. And the median is useful because it already tells something about the something more. So you could theoretically have two modes, for instance, equally high, and then a distribution between them. But here you have half of the cases on one side of the median and the other half on the other side. So it doesn't matter if it's skewed, like here you can see that this goes on forever in this direction, is more compressed in this direction. You can still use very efficient or very good description of this data would be the median, and people would understand what's going on. And then you have, you have the traditional mean. So there you count the sum of all the cases and divide it by the number of cases, and then you get the mean. And to take a step forward, in some cases, the mode, median, and mean are the same. That means typically that you have a symmetrical system, a situation here where the distribution is equal on both sides of the mean, and so it's like a mirror image of itself, and that means that in that special case you have mode, median, and mean are essentially the same. You have situations which we call skewed, where the distribution is one way of kind of leaning to one side or the other. And here you have a negative skew where the tail, or long end, goes towards the small direction of the small results. And here you have a positive skew, and there you can see that the mean is easily influenced by skew in either direction. So it kind of doesn't really represent what is typical for them. Doesn't really represent as well as median or mode what is typical for that group. And how do we get this? Well, we strive for this by measuring or if it's a questionnaire, testing it out before the real gathering of data, so as to try out that the questions are not skewed in either direction. You can easily encounter this type of a negative skew if you have a test, say a math test that is too easy. So it doesn't separate the upper end of the scale kind of easy to get less good points, and that's a long skew there. But everybody is packed in the upper end of the scale, or not everybody, most people are packed up there. And the positive skew is not positive in the sense that it would be a good thing, but it's a description of what it looks like. The positive skew you get if you have a very difficult test. So that would be a typical test where you want to select, for instance, job applicants. So you're not actually interested in this group at all. You are interested in getting the best of the best. And you would have a good reason for having a test that is positively skewed. Okay, so we have positive and negative skew, and then we have something we call kurtosis, which simply describes how peaked a distribution is. So you have the normal distribution there in between, mesokurtic, you have leptokurtic, which is peaked, like lepto is thin, and then you have platykurtic, which is flat. Like a platypus is a very strange animal from Australia with a flat nose. So it's a platypus, and this platykurtic equally is also, it's kind of spread out. You have peaked, spread out, and normal distribution. Also, we are interested not only in the averages, we are also interested in describing how spread out, how what is the variance of a certain group of measurements. So the mean tells you on a scale where the group is on average, and then you have how the variance tells you about how spread out the group is. So the easiest way of saying something about it is having the lowest value and the highest value. It's kind of can be big or small, and that already tells the reader quite a lot. But we use usually the standard deviation, which tells how similar or dissimilar within this distribution the different measurements, observations are. So again, here you have a very homogeneous, everybody is the same, and a more heterogeneous, everybody is more or less different. You could even have a situation with kind of, instead of the bump in the middle, you would have bumps on the side, and you would have a very great standard deviation or variance. So, putting it all together, you have different scales, and with these different scales, you use different measures or averages, different ways of describing what's going on, and you use different measures of variance as well. And this is important because then the way you measure the influences what kind of average and variance you can get from the data, and that again influences the methods that you can choose. We'll get to that soon, but let's just have a look at this. So if you have categorization, we had the dummy variable, for instance, boys and girls or whatever, nominal scale, 2 categories or more categories, then here the typical way of describing what is typical for that would be to say, okay, that the most frequent group in this categorization is this group, and you wouldn't have really any sense in counting some kind of a variance there. If you can organize it so that you make an ordinal scale, you have order instead of chaos, then you can already count both which is the most frequent or the mode, but type of category, but you can also count the median. So here with all these categories, half of the categories, half of the population, half of the sample is on above and half is below the median. And there you can typically use to say something about the variance. You could say, okay, is it a small range or a big range if you look at the smallest and the biggest values in an ordinal scale. And then if you can count something, even more is possible, so that you have an interval scale with equal distances between the values. In the ordinal scale, they're in order, but they don't necessarily, they can be either a long way from each other or a short way from each other. Different distances from each other is the point. In an interval scale, the intervals are the same. And if you are really lucky, you also have a real zero in there. It doesn't really matter from the perspective of statistical analysis. So mainly in education, we don't have that situation. But let's take an example where you really have a real zero. So technically, you can have an educational system which gets funding and a certain amount of funding each year, and so that would be, you have a lot of money this year and less money next year and so on. You can say something about that. In the case that we get the wrong kind of president, or we have a really serious crisis in the country, maybe we don't get any funding. That would be €0 that year. That would be really, then that there is no money. And even you could get a situation where if they are private schools, for instance, where they have to borrow, so they would have negative money. All right. Not to make this too difficult, we usually don't need to have a real zero in our measurements. For instance, when you try test somebody's skills in mathematics and they answer in the top end of the scale, then you know that they have done probably just about as well as they can. But if the result is weak, you don't know really if it's weak because they haven't tried very hard or because they really don't know math. So if they would get 0 points from the test, you wouldn't be quite sure that they are lacking in mathematical abilities. It might be, there might be some other reason for it. So it's not a real zero. Okay. And then you can use not only the mode median, but also the real mean. And you can count the standard deviation from such a scale. And we get further into the intricacies of statistical explanation. Here we have a situation. Two guys, well, you can read it for yourself. Okay, let's take a look at this. Typically, it's nice to be on the safe side, as this guy with a hat. So assuming something that is kind of safe, a safe bet means that then maybe you are not putting people in unnecessary danger. However, the world is not a safe place, and if you assume a lot of things that are not realistic, that are not supported by the data, then you also would not be able to use most of the things that we use in our daily lives based on this same logic. So here you can see people starting in the 80s to use cell phones, and the rate of cell phone use goes up to almost 100% in the United States. And then you have the total cancer incidence, which started going up in the 70s, reached about its peak in the 80s, 90s, and is slightly coming down. So if you are a researcher and you're interpreting these findings, and you make the call that to be on the safe side, I will still ban the cell phones, or recommend banning the cell phones. That means that you are protecting people from something that is very likely not the cause of the cancer frequencies. It's probably the case that people got, the population of the United States got older and older, or something else happened, and that caused the cancer incidence, and that's a different story from the cell phone using. Or simply that you have to have a better study where you really can follow the cancer incidence maybe caused by the cell phone use. Typically, however, we need to think about it in this way, that the cause comes before the effect. But just to make you think, and this is something you can discuss on our Moodle platform also, can you think of contrary examples where something that is happening later causes what is happening before? The cause comes after the effect. One way of looking at this is like school philosophy, but one typical example of this is that we are goal-oriented people, so we want to have some kind of future job, for instance, and then we make decisions to get there. And that's maybe correct. The problem with that is that it's really not, we don't have that job. We have that aim, and that aim is in our head now, and then we do something later. So our understanding of the situation causes our actions, which are goal-oriented towards the future. In this sense, philosophically, we could say that that's at least not the case where the cause comes after the effect. But if you find any good example of this, I would be more than happy for you to share it with us. All right, then we go to the next use. So these are like building stones, foundation of statistical thinking. We have the mean, the standard deviation, and we put them together here. Using them, we can count the correlation. So we are interested in cause and effect. We are interested in, if you have one thing and another thing, do these vary in the same direction or different direction, but do they have some kind of covariance? So for instance, here in this example, you have grades in English and Swedish for the same students. Do they correlate, and how can we explain, what can we learn from this correlation? All right, here we have the grades in English and the grades in Swedish, the Swedish language. And you need to know that the Finnish grading system is really picturesque, is kind of the nice way of putting it. So we have top grade is 10, and the weakest grade is a 4, where, for instance, the Swedish top grade is 5. So let's keep it simple, 4 to 10. And that's why these are so strange, these numbers here. And then you can see here I have put the whole scale from 4 to 10, and you can see each and every individual getting English 4 and Swedish 5 and so on. That would be English 4, Swedish 5, case D, and you can follow each and every one here. And then we would have something that we could say that, okay, these tend to go in the direction that if you have a high English score, you get a higher Swedish score as well. There are some higher and lower examples, but on the average this way. Sorry. And also in the other end of this, so here, if you get a low grade in English, it's more likely that you get a low grade in Swedish as well. And this can be presented as a line with so you'd have the formula of a line here with something that tells you how steep the line is. So a flat line would be 0 times x, and then how steep the line is, positive direction or negative direction would be minus 0.56 or something like this. And then you have something that tells how high this, if we had the real 0 here, how high will be the place where this line cuts the y, the 0, or x 0. So it would, x is 0, so that would mean that if x is 0, then y would be something a little bit over 2.3. All right, we don't need that anymore after this, but you get the drift here. So you can draw this picture. The problem here is, however, that the measurements that you use are this drawing, and this equation here is dependent on the scales that you have here. And this, as I said, the scales in the Finnish educational system are really rare and strange to most people in the world. So you would always have to go back and explain why the Finnish grading system is the way it is. And then they would start to understand what's going on here. Now what we have done here is we have counted the averages, sorry, the mean. So 6.17 here and so on. And standard deviation, let's see. And during this course, to your joy and enjoyment, we can use always, or you can use always the SPSS to get both the means and the standard deviations, anything else as well. All right, so here we have the means, the standard deviations. You can put them, you can see each and every individual. So the student A here, you could put what they got in English and what is the average of the group and how many standard deviations. So that would be how many standard deviation is person A from the average of the group. And that would be their Z-score. Then we have changed the from the Finnish grading system, changed into Z-scores, which means that anybody in all the world can understand this, but they can also compare the results with their own country's scores. So here already it would be easy for somebody to say that, okay, student A is more than 1.5 standard deviations above the average of the group. And student D, vice versa, would be here would be slightly below 1 standard deviation, or 1.25 standard deviation below the group average. What would that look in a picture? We would have a possibility of, first of all, counting the Pearson correlation. You can see how it's built. So we already have the Z-scores of English, we have the Z-scores of Swedish, and so on. Nothing new here. We count them all together. So the Pearson is the kind of momentum is the Z-score of student A times the Z-score of student B. We get a different picture. Now you have translated the Finnish scoring system into an international language with Z-scores, where the average always is 0 for the group, and the standard deviation in either direction is 1. This would be 1 standard deviation here. Okay. And then from that formula, you get the correlation coefficient, which is 0.69. So 0.69 times x. And you don't have to have anything else because as I said, this always cuts with standard scores. This line always cuts the origo, or 0, 0. When x is 0, y is 0 as well. And there you have it in practice. So 1 standard deviation upwards is 0.69 steps upwards. Sorry, forward 1, upwards 0.69. That would be how this angle of this line can be explained. All right, correlations are sensitive, just as average values are sensitive. Like the mean and the median, correlations are extra sensitive, let's say so. extra sensitive to skewness, actually to kurtosis as well, but let's keep it simple. So in a case where you have more or less normally distributed variables, they can correlate with each other. Sometimes they do, sometimes they don't, but that correlation reflects the connection, some connection between the variables, some real connection between the variables. But if you have a very skewed variable and a normal variable, you can try it out. But if you try to figure out how to make the cases fit into the previous kind of picture here, with the very skewed situation, then you run into trouble, because there are a lot of cases here, very few cases here. We really simplify things. So you run into a systemic situation where correlations are lowered, not because they reflect the real situation, the valid situation, so to speak, but because they reflect something else. They reflect how skewed your observation is. Now, on the other hand, skewed variables have no trouble in correlating strongly with each other. And yeah, all the way around. So, and this, you can even have skewed variables in one direction, so positive skew and strong negative skew. And in both cases, in some cases, they can correlate very strongly with each other. So if you have a very strong skewed variable measuring I love school and I hate school, both are strongly, would be strong. Let's say that both would be strongly skewed. They correlate really nicely with each other. So the kids who say that I hate school and I love school, sorry, the students who say that I hate school and I don't love school are the same kids. All right. Now, this already means something. When we work with correlations, as we will do in the rest of the course, typically we have a situation where, sorry, typically we have a situation where we can't, or we have to figure out if the skewness caused the correlations being small or big, or if it's actually the thing in itself that we are measuring that is validly presented. I'll give you one example, and this is, I think this is a shocking example. Just goes to tell you how skewed my thinking is. But I read an article, found and read an article a long time ago. It was in a really good journal, and they presented results on students' self-esteem, which I was interested in my doctoral dissertation as well. And they counted out that there is a positive and a negative self-esteem of students. And then they continued explaining and theorizing about this, while the only thing that they didn't say was that actually, if you looked at their measurements, and they had presented their means and so on, so you could see something of the distributions in their data. You could easily argue that the negative self-esteem factor came. Oh, so let's start from the positive one. The positive items of the positive scale were normally distributed. And then they had about every second item was negative, but what they had done was, if you think of it, if you have a questionnaire asking something about the self-esteem, I really like myself a lot, then if you say, I like myself a lot, then it's not anymore so easy to be of the same opinion. So it presses down the average towards something like a normal distribution. And if you make it even stronger, then you can press it even further. But that would be a typical situation. If you word it strongly, then you get a more normal distribution. Not so many people would agree that they are extremely wonderfully happy with themselves every day, all of their lives, or something like this. On the other hand, when you then, if you don't think about it, you just turn the wording around exactly the other way around. So instead of saying, I love school, I love myself tremendously, you say, I hate myself tremendously. And then you would have precisely the opposite. So typically, people would disagree strongly with that. And that would be a skewed distribution. You would see the same, same as here. Strong disagreement. And so you would have the negative items would be strongly skewed. The positive items would be normally distributed, more or less normally distributed, like here. And that would in itself produce lower correlations between the negative and positive items. And that would in itself produce a result that is just technical. It's not the content of self-esteem is not represented there. It's how you measure. And in this case, I think how wrongly you measure. Okay, continuing. Let's see how I'm doing for time. The distribution of the kids' parents have an educational background, so they have gone to school. This is the distribution of the educational backgrounds of mothers and fathers in the Nordic countries and Estonia. So from your PISA data, or the PISA data of this course, and you can see here that already something is visible. This would be how it would be if it were normally distributed. And obviously, the mother's distribution is very skewed. The father's distribution is slightly less skewed, but still very skewed. So this would be almost no education, secondary education, and here would be masters and doctors from universities. So it's a more or less ordinal scale, and you don't actually need to know too much more about that. If you are interested in how the ISKED is measured, if you look for OECD and ISKED, then they explain it very thoroughly indeed. Now then, we are approaching correlation, but we have done something else here. This is what is called a cross-tabulation. It's also something that we will try out with SPSS. Here we have the mother's ISKED and the father's ISKED, or fathers and mothers' educational background, cross-tabulated. And now you see no education and going up to masters and doctors here. So that would be primary, secondary, vocational. This would be This would be polytechnics, and here up here you would have university graduate. What can we see here? If we look more closely at this, we can see that there's kind of a diagonal here. The fathers and the mothers of the same educational level, that cell always on that row is the biggest one. Always, but mainly. And what else can we see? Well, we can see that because they are both skewed, they're kind of top heavy. So the highest education is most frequently represented in the Nordic countries, both for the fathers and the mothers. But what does this mean? At least it means that typically people get married with people or get kids with people who have more or less the same educational background as they do. If you look more carefully at this, you can also see, let's see here, that actually the women in the Scandinavian countries are slightly more educated than the men. And we have a test for this. It's called a chi-square or chi-square, and to put it very simply, it gives us a test value, degrees of freedom, depending on how many cells we have here. But the main thing here from our perspective is that it gives us also a significance. So if we test the hypothesis that there is a connection, covariance between the education of the men and the women in the family, we find that that hypothesis is strongly supported. So if we make the assumption that there's no connection, the risk we are taking of being wrong is extremely high. Or if we accept that the connection is there, this diagonal is real, then that would be strongly supported by this. So we can, when we see this, that would be if it's a 0.01, that would be a 1% risk, 0.05 would be a 5% risk, 0.000 means that it's less than 1 promille risk, that's less than 1 in 1,000. So very, very small risk of being wrong if we say that there's a connection between these two things. Going on. What does it look like? Oh, sorry. Whoops. Connection. For some reason, I put this here in between. I was going to do this. Sorry. We'll get back to that picture. It's a nice one, but it doesn't. It's about a different story. Anyway, the real correlations we use would be different from the chi-square. So we have, in the case of correlations, we have the Pearson's correlation, which is a typical one, and then we have the Spearman's rho. So Pearson that would be what we typically use, and that would eat or use variables that are normally distributed and typically where the different values on the scale would be equidistant. As you saw already, that's certainly not the case with the mothers and fathers' education. So this is really, really bad choice for counting the correlation. A better one, a very good one, would be Spearman's rho, which allows us to have ordinal scales, and it doesn't matter if they are normally distributed or not. Actually, it doesn't matter at all. And then it produces a correlation coefficient. However, when we compare these two correlation coefficients here and here, you can see that they are almost exactly the same, and the significance is almost, well, it's exactly the same. You would have to have so many decimals that it doesn't matter in the world or real life. So what can we say? Well, we can say that nothing very, very strange or bizarre or dangerous would happen if you use the chi-square to describe the connection between the fathers and mothers' educational level of education, if you use the Pearson, or if you use the Spearman's rule. And sometimes you see with master theses and doctoral dissertations, you see that people have been worried about using the wrong kind of measurement, the wrong kind of statistical tool, and then they report something like the Spearman's rho in this case is 0.44. The significance, let's get back to the one-tailed, two-tailed significance, but the significance is less than 1%, say. And then they say we also tried out the chi-square and it said the same, or we also tried out the Pearson and it said the same. So people have been worrying unnecessarily, I think, because during these studies you will learn to say the correct measure, but if or method. But if you use another one and find yourself in trouble or worried about the result, check it out. You can use different approaches and try out the same thing and see if you get the same. So if you really have a valid, real description of your data, then it should be fairly robust. So it doesn't change totally just because you use a slightly different approach. But of course, as this is a master's thesis we are talking about, you should be trying to get the correct method for the correct procedure for the correct thing. It's obvious that that's a good idea. But maybe this gives you some kind of idea that this is not the most dangerous thing in your life. They give the same result. Okay, the one-tailed, two-tailed story. Simply put, if you have a correlation where you have a two-tailed significance, then they can either be in the same direction or in opposite directions. So the correlation would be either strong positive or strong negative. However, if you test a one-tailed, then you select, the idea is typically that probably, and from previous research, we could think that probably the parents select each other, and one of the places where they select each other is a university, and so they have a tendency to be more of, or the workplace, more of the same, on the same level in their education. So that would be a one-tailed hypothesis. T-test. Now, I remember the picture that we have here. I put it in the wrong place, but this is the story here behind this. So T-tests and other such are interested in, is there a difference between the average or the mean of one group and another group? So here, if we look at the girls and boys in the Nordic countries and Estonia, is there a difference between the boys and girls? So here we have the distribution of the girls, fairly normal. Distribution of the boys, fairly normal. Slightly, how would you say? Would you say that they are the same or almost the same, or are there some differences? Well, if you look closely, you can see that there may be something going on here. So more boys with lower values here, slightly more girls with higher values over here. Something of that kind. Maybe even that they're here on the top of the distribution, the boys have a slightly sharper distribution than the girls. We don't know. So already from this, we could say that the distributions are more or less the same, but there may be slight differences between the groups. However, if you look at the average of the group, it would seem to be very much the same. So do they have the same math performance, girls and boys in the Nordic countries? The answer would be, from looking at this picture, yeah, pretty much. Let's try this out with a t-test. I'm going there. Okay, here we are. Students' independent samples t-test. Independent samples like boys and girls, or people from your experimental group and your control group, or whatever. This kind of groups that don't have anything to do with each other in the sense that you can't belong to both. Well, with gender, you are not so sure about that anymore, but that's a different story. Here we do take the simple route because they have measured it only this way. Okay, what do you see when you put gender as the explaining factor into a t-test and the PISA math factor as the dependent variable? Well, first you see precisely what we saw with our own eyes previously, that the difference between the boys and girls is extremely small. We also see something else, sorry, up here. That already tells us slightly some difference in the distribution, in the standard deviation of the groups. Not much, but some. And that comes in here. So t-test is really nice because it helps us here. It's supposed to be testing groups that are of the same, have the same distribution, same variance. And it has this Levene's test for the equality of variances first. So it tests if what we see here is something to worry about or not. Here it says, yep, you should worry about it. So it's a significant difference in variances. From that, you go down to the equal variances not assumed. So because there are significant differences, you don't assume them, and the test is built, rigged to give that answer. If you would have a non-significant result here, you would go here. But actually, again, you can see that the significance you get here is pretty much exactly the same. If you had decimals again, like 6 or 7, you could get a difference, but it doesn't matter in this world. All right. So how do we read this? The variances were not equal, and the t-test tells us that the means of the female and male groups are the same. In practice, they are the same. No difference, slight difference in variance, and no difference between where on the scale the group is. There you go. And what's this? Already a third way of doing the same thing. So here we have the independent samples Mann-Whitney U-test. So if you can't use the t-test because it's the distributions were so skewed or something like this, then you use a non-parametric test, a test that it doesn't assume normality, doesn't assume that you have the correct type of scale and so on. And here again, it's you learn this in the workshops, but typically you get exactly the same significance here. So the significance is still not significant, and that means that again, one more time, there's no difference between the groups. Actually, you can do something fun with this. If you click in this corner here, double click, sorry, that's the significance. Double click over there, it brings up this picture and some statistics, further statistics, but this one is nice, so you can really easily get out a comparison between the groups, and you can observe that actually their largest values here are the same and the distribution is more or less the same. This is not always the case. Sometimes you can see with your eyes that there's a clear difference, and that already convinces you that okay, what we see. It also helps if there would be a difference here, you could then say, okay, the boys or the male are more good in math than the girls, or vice versa. Not so here. And now I'm getting very close to the finale here. We have gone through this. So this is basic quantitative methods are scale dependent. So if you have two nominal variables, you can do the cross tabulation and chi-square. Two ordinal variables, you do Spearman's rho correlation. Two interval scale variables like two interval scale variables like the parents' educational background, you get the Spearman typically. If you have two interval scale variables, but you don't have a normal distribution, you go back in the same way to Spearman's rho. However, if you do have normal distributions in both cases, then Pearson's correlation would be advisable. And then if you have dichotomous cases, like boys and girls and so on, two classes, and a non-normal distribution like we didn't have in our example, then the Mann-Whitney U-test would be recommendable. If you have a normal distribution, then the student's t-test is what you are aiming for. So that concludes this part. We have methods for every kind of emergency or need. And here in the same way, I'm trying to explain what's going on in the rest of the course. So we have situations where we have many correlating interval scale variables. What we are interested in is to see how many dimensions we need to. So can we compress this into just one factor, one dimension, or do we have to have many dimensions to explain the variance of these variables? For this, we typically use the factor analysis, but it's connected with what we do with the item analysis package as well in SPSS, where we can check the reliability of the scales we are using on the test. If we have two or more interval scale variables, then we can do nonlinear covariance, and sorry, then we can analyze if it's nonlinear. Sorry, if it's nonlinear, then we can have a linear regression analysis. So typically, in the case that we were talking about, the connection was linear, can be positive, negative, or flat line. But if it's nonlinear, it could be looking like an S or some kind of squiggle. And then we would try out nonlinear models of regression. We don't do that, I think, during this course or just in the very end of it, depending on how much time we have. Sorry, here's a spelling mistake. That's Finnish, but if there's a linear relationship, then we use a regression analysis to get an understanding of this. So we are concerned with a relationship between two or more variables, and we can have many variables that explaining something. And more Finnish. I have been clearly tired when I did this. Okay, so one or more nominal scale variables and one explained variable that is continuous. And then we have either in the normal, non-normal, or the normal distribution again. The idea here is that we try to get to, if it's normal, we use analysis of variance. And if it's not, we have the non-parametric variant, which is a Kruskal-Wallis one-way ANOVA. So here, not only difference between two groups, boys and girls, but between many groups. All right. The idea with these videos is that you can stop them anytime you like. You can look up the stuff you want to clarify. Google, Wikipedia, and especially YouTube have wonderful demonstrations of the different methods and explanations of the different terms we are using, and so on and so on. If it helps, that's great. So I'm the kind of teacher who tries to make himself unnecessary as soon as possible. If you become expert, if you find the stuff that you need, if you can do the analysis that we are trying to get done, understand what you're doing, that's perfect. I don't need to be the one who's saying everything. Please remember, however, that we are actually a community of learners, of researchers in the future. You will hopefully become a research community also, so that wherever you are in the world, you have always the backing of your fellow students, your alumni friends, and learn as soon as possible already on this course to share what you find, all the good stuff that you find, put it in our Moodle, discuss it with the friends, and tell about it. Because together we are so much more than as individuals. And in research, that certainly goes. So there's not a single one of your professors who doesn't stand on the shoulders of giants, people who have actually invented the methods that we are using, who have invented the theories that we are using, and so on. So it's very humbling in one way, but it's also tremendously enabling. It opens up the possibility of thinking in a way that no individual in the world would have thought of alone. That's why we are so much more together. Thank you very much.